Good morning, Eamon Darcy is my name. I'm the founder and operator of QEQA, the Quantum Education Centre of WA. And today I'm going to talk about quantum teleportation, you know, the beam me up Scotty type Star Trek made famous. Now, you're going to think, oh, it's so advanced and this, that, and the other. And I'm here today to prove to you that if you have a very basic knowledge of quantum computing, it's dead easy. It's incredibly easy. And I don't say that with any other objective than because it's the truth. And I'm going to prove it to you. You do have to have the basic knowledge, but if you've got and I mean the basic knowledge of quantum computing, you'll be able to do this. Currently, I've written a course for 9 to 12-year-olds in the UK. If they did that course and did it assiduously, I can promise you my next course on quantum teleportation, they'll get it, and they're 9. Okay, let me share my screen. I'm sorry about this, what's happening? That's better. And that's better. Excellent. So, quantum teleportation. I'm going to tell you what it is because there's a few different ideas of moving an object from one place to another. The final effect is that something moves from one place to another a long way away, and there's a few different ways it can be done. My second point, I'm not going to shy away from this, it is simple. Third, I'm going to show you creating and sharing a thing called a Bell state, which is basically just built on quantum entanglement. I'm assuming you understand quantum entanglement and superposition. And they're going to tell you how quantum teleportation is done conceptually, i.e. in the one laboratory. So if we didn't have any encumbrance of distance, how we could move a atom from one place to another. And then I'm going to show you the reality of it. And by the way, it has been done. It's now been done many, many times. China actually did a quantum teleportation between their laboratories. I think it was Beijing, doesn't matter. Their Earth-based laboratory, and they did a quantum teleportation to an orbiting spacecraft called the MICIUS, MICIUS. Please Google it. And then there's been many more done. Even now, drones are teleporting to each other. It's the future, and the time to know it is now. Okay, so what is it? So look, basically there are 3 types. One where something magically goes through a loophole, a fabric of space-time. 1 minute's there, pow, next minute it's gone. No one knows why. Bermuda Triangle, do. And we're certainly not going to be covering that today, but we're not going to knock it out. I just wanted to mention it. Secondly, which is the Star Trek way, is you know the way you disassemble every single atom in an object and then send those atoms to the object, to a different location, and then they're reassembled. That's what happens in Star Trek. But with quantum entanglements, this is what we do. We scan this object and send the instructions. We send what's called the quantum state, the complex amplitudes. You know, the psi, the wave function, which is psi, equals alpha ket 0 plus beta ket 1. Alpha and beta are the complex amplitudes. It's amazing. We can send them to somewhere a long way, almost out of this solar system. There are constraints, which I'll tell you about soon. But we can do it, you know, so easily. It's unbelievable. And we do it with, we cannot look at the atom. We cannot measure the subatomic particle. Because if we do that, it will collapse the wave function and ruin everything. So we have to be clever. We're so clever. The physics community, the theoretical physicists that I have the honor of reading their work, which I do almost constantly. It's an honor to be able to read the thoughts and the things that these people do and come up with. The original is always destroyed due to the no cloning theorem. There's a proof of the no cloning theorem, but I won't go into that today. Just trust me, if it goes from one place to the other, it has to be collapsed in the original place, so two won't exist at once. It's a fundamental way of quantum physics works. And I want to say something else, because people keep saying, oh, it's faster than light, and you could be on, we could go from here to Jupiter and do it immediately. Let's be clear, we have to send classical bits to do a quantum teleportation. And that means a 1 or a 0. And we can do it over the phone. We could do it through fiber optic, but we have to do it. You have to send classical stuff, so there's no faster than the speed of light. It is surprisingly simple. Who knows these 4 gates? These are the 4 fundamental gates, quantum gates. They're there's nothing more basic than these 4 gates. You've got the Hadamard that puts the qubit in a superposition. You've got a C0, which takes a control qubit. If the control qubit's 0, it leaves it alone. If the control qubit's 1, it flips the other qubits. And then you've got the Z gate, which is a phase flip, and then you've got the X gate, which is a bit flip. That's it. That's all you need to know. And even more than that, I'm going to show you the mathematics behind it. I'll just get my pointer. So we have the X gate here, the Y gate, the Z gate, the Hadamard gate, and these are the matrices that's involved. Look how basic they are. Look at them, they're so basic. These are the basic gates. C0 is slightly less basic, but it's still basic. You've got to remember, on the qubit's in a state, then it goes through a gate, and then it comes into another state. So you've got the pre-state, the quantum gate, and then the post-state. It's only multiplying out. If I've got a gate that's a 0, and I put it through the X gate, if you multiply 0, zero's a vector, 0, 1, but don't worry about that. If you multiply initialize the 0 state of the qubit by 0, 1, 0, 1 here. Oh, I haven't got my pointer on now, but don't worry. That's all it is. It's just a multiplication. It's just one multiplied by the other, and then the qubit changes its value. And we still can't measure it, but we know what that value is. Now, this is the whole quantum teleportation protocol. You will understand this at the end of this presentation. You will understand what this is. And I say that simply because it's the truth. And I'm gonna go through it. Don't worry if you don't understand this, because you're not meant to. I haven't done the presentation yet. But I just want you to show you how easy it is. Alice wants to send a quantum state, the wave function, that is psi there, and he wants to send it to Bob. What Alice does, Alice has 2 qubits and Bob has 1 in his laboratory. So what she does, she simply puts a C0, and these 2 qubits share a Bell state, which is that formula, which I'll explain. Alice just does a C0 and a Hadamard, and she measures them, And then she tells Bob, who remember has this bell state, shares a bell state. She tells Bob, look, Bob, I got a 1 on my first qubit and I got a 0 on my second. And depending on what he's told, he will change these gates. He'll either do nothing or change gates. That's it. And then psi magically equals the psi that we started out with from Alice, automatically goes to Bob, no matter where he is. It's unbelievable. It's unbelievable that it's so, straightforward. Okay, I'm going to now show you creating and sharing a belt state. Not difficult again, but I don't just want to say they share a belt state and you think, what the hell's that? Because Alice and Bob have to share a belt state. Now, a belt state is merely a Hadamard gate times a C0 gate. Now, and then it's in a belt state, and there are 4 belt states depending on what these original qubits are. Give me a second. So we have now got 0, 0. So the first qubits, a qubit is this line, by the way. So this is the first qubit, the control qubit, and this is the second qubit, the target qubit. And at the moment, they're all initialized to 0. Normally in quantum computing, when you start off, it's initialized to 0. But even if it was different, we would still have a belt state. It would just be a slightly different one. How can it be so simple? These 2 gates, which when you learn quantum gates, these are the first 2 gates you come across. But I'm going to show you even the mathematics behind it. I'll show you the mathematics behind it for when they're both initialized to 0. So if we take this product state, what we're going to do is multiply this state by this qubit state, by the quantum state of this qubit, by the quantum state of that qubit, before the C0. That's why I've got that line there. Put the C0 to one side. I just want mathematically to know what's the mathematical formula for this before we go to the C0. And it's dead easy. You may or may not know, with a Hadamard gate, when you multiply it by a qubit that's on 0, it gives you 1 over square root 2 0 ket plus 1 over square root 2 ket 1. Now that might sound complex if you don't know what a ket is, or 1 over 0. Honestly, study it for 15 minutes and you'll be okay with that. That's what a Hadamard gate does. Incidentally, if it was initialized to 1, then that would be a minus. That's only the difference. So here we are with this here equals those 2. So we have to multiply by this one. So that's the ket 0 here. So these are what are called tensor products when they're all multiplied out. So if you multiply the ket 0 by these 2, you get 1 over square root 2 0 0. This is the first qubit, the control qubit. This is the target qubit. And then you get plus square root 1 over 2 1 0. So these 2 represent the first qubit, the second qubit. This one is that one. This one is that one. I've multiplied them across. Beautifully done. And now, so that's what that equals. Now I'm going to multiply by the C0 gate. Now with the C0 gate, as I said to you before, C0 gate's very simple. All it does is it checks the control qubit, and this is the target qubit. Now it says, are you a 0? If you are, I'll let you go. If you're a 1, I will change this one no matter what it is. So if it's a 0, I'll make it a 1. If it's 1, I'll make it a 0. And remember, this is the first qubit, second qubit. So when we multiply by the C0 gate, which if you remember those matrices I showed you before, not difficult, but what it will do, the first one here is a 0. So we'll leave the second one alone. But the first one here is a 1. So the CNOT, the control qubit says, hey, hold on a minute. If you're a 1, I'm going to change the second qubit to a 1. I'm going to flip it. So change it from a 0 to 1. And this is what we call a Bell state. 1 over square root 2, 0, 0 plus 1 over square root 2, 1, 1 is a Bell state. And it's called the phi plus state. That's just the name of it, and that's what it is there. Now, I said to you, Alice and Bob share a Bell state, and you go to any laboratory, any third party could create a Bell state with 2 qubits, and then send one to Alice and one to Bob. And they would have, and so they could be photons. When I say a qubit, it could be an electron, a photon, an ion, a quantum dot, a photon. Did I say that? So they're dead easy to prepare and share. I've now shown you how to do this particular one. There are 4. And I'm not going to go through each one, but remember it was 0, 0 before, now it's 0, 1. All it does is it changes the math slightly and creates. So here we have the 4 of them, which just, you can see they're very slightly different. Minuses here, and that's why they're the plus and minus. It doesn't really matter. You create a Bell state on 2 qubits. It has to be. It's a 2 qubit thing. It can only exist on 2 qubits. So that's how easy that was. And the Bell states, they're called Bell basis states, and they form what's called an orthonormal basis. And all that means is it's when the beauty of quantum computing is that when you add qubits, you actually add them exponentially. And they create this bigger dimensional vector space. As I said here, so it's 2 to the n. So we've only got 2, so it's 2 squared, which is 4. But that's how it's so much better than ordinary computing. But I want to get into the exciting stuff, which is, I'm going to tell you if they were all in the same lab, conceptually how it could be done. So this is psi, the wave function. We want to send a qubit to Bob from Alice. Alice does not know the values of alpha and beta, because if she did, they would collapse. So she can't know them. How can she send them to Bob? Unfortunately, you can. This is how easy it is. So let's say they're in the same channel. Now, as this, I get my thing back up. So this is a CNOT gate. Now, if they're in the same laboratory next to each other, and I mean very close to each other, qubits have a problem when we have 200 of them, how to do a CNOT gate between the first and the 100th. And they're actually, they actually do it through error correction and la-di-da-di-da. But talking about doing it like if somebody's on the moon and somebody's in a laboratory, you cannot use the CNOT gate. But I'm using it here so that you understand the way it works. So here's Alice's bit. Remember, it's a wave function, alpha 0, beta 1, and here's the 0 for the second bit, Bob's bit. Now, if I multiply them out, the product state, it's just going to be alpha 0, 0, beta 1, 0. And what does the CNOT gate do? Well, as we know, it changes the second qubit if the first one is in a 1. So because it's a 1 here, you add the 0, it becomes a 1, 1. So we've got here alpha 0, 0, beta 0, 0. And this is an entangled state. Now, but that's not what we want. What we want to do is replicate this function here. So we could measure this. Now, there's a couple of there's a few measurement bases. First of all, there's the computational basis, which is 0 and 1. But if we measure it in 0 and 1, we either get the first one is a 0, but then if the first one's a 0, because they're entangled, the second one will be a 0. If it's a 1, the second one's a 1. So it's nothing like up here, which is what we want. But what we can do is measure in what's called the sign basis. And again, you may or may not be familiar with it, and it's new at first, but the sign basis is just dead easy. It's just different way, instead of 0, 1, it's a different way around the block sphere, but we won't go into that. All you need to know is that we can substitute something for 0 and substitute for something for 1. It's actually the Hadamard basis. So it's instead of 0, 1, it's plus minus. So now we need to take this, but we need to change the first qubit, i.e. this one. We need to change the 0 to the plus. And 0 equals, when it's measured in the Hadamard basis, it is alpha 1 over square root 2 plus 1 over square root 2 minus, it sounds complex, but it really isn't, tensor ket 0, which is this one here, plus beta 1 over square root 2 plus minus, whereas it's plus here, it's minus here, because when you apply it to a 1, it's minus, 1 over square root minus tensor product of 1, because you've got to multiply by the 1. Now, if you multiply them out, it comes to this. We don't, you can multiply it out in your own time. And it eventually comes to this here, which is the state measured in the Hadamard basis. Now, if you get let me get my trusty pointer, so you know what I'm referring to. Let's say you measure it and Alice gets, so she's now going to measure her part of the bell state. If she gets a plus, she's going to be left with alpha ket 0 plus beta ket 1, which is exactly what we want. It's psi. It's exactly the same as up here. The beauty of if it was quantum, and if it was just entangled quantumly, then if you collapse one, the other one would collapse. But because it's in a bell state, you can collapse your bell state, but it doesn't affect the other bell state, and then you can reverse it if you know the basis that it was measured in and what it ended up as. And that's what Alice will tell Bob. She could actually just phone him up, or she can send it through fiber optic. This is where the limitation is. Technically we could send it to Voyager 1 and Voyager 2 if there was someone there that could receive it. So if it's a plus, and she'll say, oh, Bob, I got a plus. So just leave it alone, it's psi, it's all worked out magically, quantum entanglement, yoo-hoo. If she says a minus, look, Bob, I got a minus. Now, all that means is you have to do a phase flip. Don't worry about what that means, which is a Z gate. So, Bob, I got a minus. She's on the phone. I got a minus, Bob. Do a Z gate and we're all right. Can you believe it's so simple? Now, in reality, okay, same thing, but now we can't do a CNOT gate because we're sending it to the moon. So what she does, remember, so look, we've got 3 qubits here, 1, 2, 3. Remember, 1, 2, 3. This signifies the different laboratories. Oh, sorry, I haven't got I keep forgetting to put my annotation thing on. Qubit 1, qubit 2, qubit 3. Here's the line, the demarcation line between the laboratories. This is Alice's on Earth. This is Bob's on the moon. But they share a Bell state, which is the phi plus state. That could have been any of the four I showed you before. No big deal. Look, no complication here. She does a C naught with her qubit and with her 2 qubits. So she's got 2, Bob's got 1. She does a C naught gate with her part of the shared Bell state. Now, this is what the 3 qubits look like. So this looks far more complex than it is. Please trust and believe me. This is psi, and this is her part of the Bell state. Multiply them all out, you get that. And then remember the C naught gate, apply that, and you end up with this. You know, it's a very, very basic mathematics, nothing to it. I did want to show you, and the other screen I had alpha square root 2, 0, 0, 0. Please realize that the one on the left is the first qubit, the one on the right is the third qubit, or however many you have. It goes from left to right. Please don't make the mistake of thinking that the one on the right is the first qubit. And so we've just multiplied them out, and we've multiplied by the C naught gate. That's where we were. Now, if Alice measures a 0, and remember, the one in the middle is Alice's shared Bell state. Remember the 3 qubits, one all on top of each other, the middle one, and that's the middle one here, middle 0, 0, and here is 1, 1. So if we do measure that as a 0, what we do is Alice does a measurement. Oops, sorry. She does a measurement, and then takes, her measurement will leave. If hers then collapses, she's now got alpha 0, 0 plus beta 0, 0, which is a Bell state. And likewise, if she measures a 1. So let's put it all together. So here's here's the first qubit, the second qubit, the third qubit. We do a C naught gate between Alice's qubits. Then we put a Hadamard gate. The Hadamard gate is just measuring it in the Hadamard basis or the sign basis. That's what it's doing. This here means measuring. So it's not a gate as such, it's a measurement. So what happens is Alice puts on a C naught gate, she measures it, and then she calls Bob, and she said, I got either a 0 or a 1. And he'll either do nothing or apply a next gate. And then she measures her other original qubit, which is psi, and then she says, oh, Bob, I got a 0 or a 1, and he'll say, okay, I'll let it go, or I'll do a Z gate. Oh, I said Z gate, didn't I? That's so American, sorry. A Z gate, and then miraculously, it comes back to psi, and that there is exactly, in every way, the same photon, electron, subatomic particle that is in the other laboratory. And this could be on the moon, orbiting the Earth. It could be on Jupiter. It could be anywhere that we can classically contact, because we need to sell them the 2 bits of information so they can make the decisions here. Now, so what's happened? Alex has originally a qubit with 2 complex amplitudes. She can't look at them, but just by supplying 2 classical bits, we've somehow implicitly teleported this incredible reconstruction of a photon, electron, subatomic particle millions of miles away, and that's the power of entanglement. Now, I mean, that's just pretty amazing, isn't it? I hope you enjoyed that. I've presented on this many, many times. More than happy to take questions, and take care.